In this problem, we're told that enough of a monoprotic acid is dissolved in water to produce a 0.0134 molar solution. The pH of the resulting solution is 2.56. Calculate the Ka for this acid. So we are given initial concentration, and we're given information to find the final concentration of our hydronium and our conjugate base. So it's clear we're going to use an ICE table. So here the charges aren't quite showing up, but here is the generic equation for any weak acid dissolving in water. It's going to form hydronium and the conjugate base. Here's our ICE table with our initial concentration, the change that this acid has to undergo to establish equilibrium. It has to shift to the right, losing concentration here and gaining concentration on my product side. And then my equilibrium row, my last row, is the sum of the first two rows. So here is my equilibrium expression with the concentration of my products multiplied together divided by the concentration of the weak acid at equilibrium. Now I'm given that the pH is 2.59, so that allows me to calculate the concentration of my hydronium. My hydronium is going to be 10 to the negative pH, or 2.57 times 10 to the minus 3. So once I know my concentration of hydronium, I also know my concentration of my conjugate base, since they are equal to one another due to a stoichiometric coefficient of 1 for both. So I plug this value for my hydronium concentration, and I also actually know what X is because that is equal to hydronium. So now I can plug in my value of X to all my equilibrium concentrations and calculate Ka. So hydronium and my conjugate base are both 2.57 times 10 to the minus 3. So when they're multiplied together, that's the same as squaring. And then my acid is the original concentration minus X, which we've already determined is 2.57 times 10 to the minus 3. So when I let my calculator do the math here, I get 6.1 times 10 to the negative 4 as the Ka value.